Thank you. Well, today what I'd like to talk about, it's, as Tara said, is a condensation of what I had, or a condensed version of what I had presented in Aberdeen, and specifically just looking at reproductive potential, what those biological parameters are, and how they directly are used in calculations for reference points. And looking at this outside of a stock assessment so that you are really just isolating variability and reproductive potential and seeing how that translates into uncertainty in the reference points. We've all seen a number of talks that have categorized the different ways to approach reference points. I lump them into two categories. One is calculate a stock recruit function, and then your estimate of steepness determines how resilient your stock is, and that's what drives your reference point. The other approaches are all some sort of proxy reference point. For example, percent SPR, which is spawning potential ratio, F0.1, Fmax, etc. If you have informative stock recruit data, then taking the first method makes sense. However, it's more often the case, as we've heard over and over, that your stock recruit data are not informative. And in this case, people either resort to specifying priors to constrain the solution for their stock recruit curve, or else they just use a proxy reference point. I'm going to be using a framework for the reference point calculation, and I won't go into the derivations, but just summarize the main conclusion is that there is an analytical relationship between SPR and steepness. Because of this analytical relationship, if you have to specify a tight prior on steepness just to be able to estimate a stock recruit curve, specifying that tight prior amounts to specifying your reference point. So in fact, it's not any different from just using the proxy method where you specify a percent SPR. One slide with an equation, this analytical relationship between SPR and steepness, which I've abbreviated H here, because there's also a relationship between steepness and the maximum reproductive rate, we can express the spawning potential ratio either as a function of steepness or as a function of this maximum reproductive rate. This maximum reproductive rate was defined by Myers et al. That's this second equation on the screen. And just highlighting what those two components are for the maximum lifetime reproductive rate. It's the product of two terms. The first term, the green one, A, is the slope at the origin of the stock recruit function. This is density-independent recruit survival. The second term is unexploited spawners per recruit. So it's your lifetime reproductive output. I think using this parameter where you have those two components, recruit survival and then lifetime reproductive output, I think it helps to conceptualize why it's so difficult to estimate steepness or alpha hat in a stock recruit relationship. You can imagine all of the things that influence the slope at the origin: environment, temperature, oceanographic currents, predators. And then this other term here, unexploited spawners per recruit, which is, I think, kind of the focus of this workshop, this working group, highlighting changes in fecundity at age, maturity at age, and then anything else that affects natural mortality. So what I'm going to focus on is right here, the fecundity and maturity, and discuss the variability and reproductive potential, and then look at how that affects the reference points that you estimate. So one of the factors, maturity at age, this is a probability based on either your age or size. If you have a microscopic determination, you may be able to incorporate estimates of the fraction that skips spawning in any particular year. For fecundity at age, some sources of variability may be related to experience, which might be correlated with age of the spawner. May vary based on the condition of the spawner, which may be an environmental effect. As a number of folks have identified as well, It's rare, at least in the assessments that I've done and been involved with, to actually have egg production. So most often we do use weight as a proxy here. We use weighted age, and in most cases, we have that estimate each year. So if something's affecting the weight of the spawner, it may also affect their condition. Whether or not that scales linearly is hard to say if you don't have the data. Finally, mortality. This can vary based on the age, size, density. It can vary by year, environment, predators, and also fishing mortality, depending on the selectivity and the size of the individual. So each of these biological factors I think of as a function. So maturity is a function of age, year, the fraction that skip, and anything else that might affect maturity. Fecundity, also a function of age and year, condition, experience, etc. And then mortality, age, year, density, environment, and fishing. For this exercise, I'm just going to assume 0.2, again, because I just want to isolate how variability in these two terms translates to uncertainty in the reference point. So now I'm just going to go through a quick example. This function of maturity, I'm just going to consider as a vector at age. So each of these is the proportion mature at age for a given year. And then I'll think of skipped spawning as a vector, a scalar vector that modifies this null maturity vector. So if there's no skipped spawning, 1 minus this gives you your original vector. If there is a fraction that skips spawning, then you would multiply those. These numbers I made up. I don't have data to guess what they might be, but this is an illustration. And then if we look at how that affects not having skipped spawning versus having skipped spawning, you see the curve is a little bit lower, but not tremendously so, primarily because I put the greatest fraction of skipped spawning at these younger age classes. That seemed reasonable, but they also had the lowest maturity to begin with. The second component I wanted to consider was fecundity. Again, the same sort of schematic where I have a vector of fecundity at age by year, and I've scaled these to 1, so they're relative. And then I have a separate vector that scales this based on condition, whether it was a good year or a bad year, and experience, so that older spawners have used their experience to achieve greater fecundity. So here's condition, multiply it by 1 if there's no effect. If it's good condition, it should be greater than 1, and if you have a bad condition, less than 1. And then I have a trend related to age. And then for experience, again, the effect of no experience versus if experience matters, then the fewer times you have spawned, the lower your realized fecundity would be. And as you would expect, black being the null curve here for no effect, the only two curves above that incorporate in red good conditions, and in blue having experience, but again, that only helps the oldest ages. All other combinations related to either bad condition or having an age effect for experience would lower the realized fecundity. So now just a simple evaluation. I'm taking route 2. I'm going to specify a proxy reference point looking at an SPR of 30%, and then calculate the reference point for each of the null vectors, as well as all permutations of the maturity and fecundity scalars. And what I want to look at is how this parameter phi0, which is the unexploited spawners per recruit, how does that vary with each permutation of the maturity and fecundity scalars? And then given that, how does that affect your estimate of the F that produces 30% SPR? And then given that those ranges of Fs, what is the final impact on the yield per recruit that you estimate? So again, this was the relationship. SPR is a function of this alpha hat, which was these two terms. Given any two of these quantities, you can solve for the third, so I've specified this to be 0.3 I can calculate this one, because that was that equation in terms of fecundity, mortality, and maturity. And then it's simple math to get this third term. Going through the calculation to look at the effect on unexploited spawners per recruit. First, the dark blue, this set of bars has the null maturity vector, and the light blue has the effect of skipped spawning. And then within each of these blocks, I've incorporated good condition here, bad condition, experience, good condition and experience, and bad condition and experience. So you can see, compared to the null case with no experience or condition effect, that you really only see higher reproductive potential with good condition. That's the main effect. Comparing the dark blue to the light blue bars, there's almost no difference between the height of those bars in each of the corresponding categories. So now taking this unexploited spawners per recruit and calculating the F to get a 30% SPR, this is the same comparison. Dark blue, straight maturity. This light blue has skipped spawning. You can see there's some range here, roughly 0.34 to 0.3. And again, the biggest effect between bad condition and experience versus not modifying those curves at all. Finally, taking those values of F and taking it the next step to look at how that impacts yield per recruit, you can see that there's very little variability between the bars within the dark blue and also within the light blue. So we've dampened even more the effect of that original variability between each of the vectors. So each bar in that plot represents a reference point for any given fixed input value. So for instance, if you knew good condition was occurring in a given year and there was no skipped spawning, this would be your yield per recruit reference point. In a different year, with good condition but skipped spawning, this would be your yield per recruit. So that would be the case for a fixed realization in the environment. And you can conceive of this serving as the basis to characterize your uncertainty in the reference points. So in what follows, I'm going to show what those distributions look like. Here you have the range in F. Most of the observations fell between 0.29 and 0.31. A few observations out here, that's just showing really the range of the bars. And even more tightly compressed, 0.121 to 0.126 for the yield per recruit. So the point of this simple illustration was to demonstrate how the biological parameters contribute, in a calculation sense, directly to the reference points. The uncertainty in those final two histograms actually give equal weight to each combination of the biological inputs. In reality, what you would want is some estimate of how frequently each of these processes occurred so that you could weight the outcome. In addition, you would also need to constrain some of the combinations. For instance, you probably wouldn't expect good condition and skip spawning to occur in the same year. I looked at all possible combinations just because it was easiest, but not knowing how frequently or which ones to censor, that's something you would want to be able to characterize in order to give a realistic distribution of that uncertainty. Normally, these sorts of calculations would be part of a stock assessment where, I think as we saw in Paul's talk, the overall model uncertainty, as well as the strength of information from your age composition, more often than not swamps the uncertainty due to your reproductive potential. Another important point is, so we've been talking about how do you estimate what spawning potential is, but another key component of stock assessments is when the stock is overfished, you have to rebuild and give catch advice for rebuilding. And so it's very important in those projections to be able to say what the biological parameters will be. And it's not perfect what we do now. We assume it'll be similar to the years that we've just made the most recent observations. But incorporating more biological realism also then forces you to say what will those biological realizations be in the future. So that's another, I think, important point to consider. And that's the last point I wanted to make, if there are no questions.